KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, first we start with example 7.5. Okay. In this example 7.5, he has given one vector, right? Sorry, he has given two vectors, no? Because one is force vector, another one is position vector. Asking to find a torque, right? Find the torque of a force. Find the torque of a force 7I plus 3j minus 5k about the origin, right? Full stop. The force acts on a particle whose position vector is. The force acts on a particle whose position vector is, right? That is what I minus j plus k, right? And that formula we know, that is tau is equal to r bar cross f bar, right? And there are two methods. One is linear method, but here we are solving the problem in determinant method. That is what determinant rule, right? So by writing like this ijk, and first this is one vector, that is what r bar, and this is another vector, that is what 7, 3 and minus 5. Okay, and you know that how to get the product of this, that is what r bar cross f bar. And first you know, it is I into, it is what 5 minus 3, because minus into minus plus, no. So 5 minus 3, it will be 2 ma. Next you know, j is going to close, right? And here you have to take that, this is what reverse, you know, this is what 7 minus of minus 5, you know, 1 into minus 5 means minus 5, no. 7 into 1 means 7, no, right? 7 minus of minus 5, right? That is what 7 plus 5, that is equal to 12. That is equal to 12, right? It is 12, and then here it is what, ma? 3 minus of minus 7, it is what 10, right? 3 plus 7, it is 10. So 2i plus 12j plus 10k, 2i cap plus 12j cap plus 10k cap, right? So this is what the resultant of r bar cross and f bar, right? So if you get the vector product of two vectors, what they have given, and the resultant of those two is this one. Okay, right. Next problem, that is what example 7.6. See here, show that the angular momentum, right? Show that the angular momentum about any point. Show that the angular momentum about any point of a single particle, moving with constant velocity, remains constant. Okay, show that the angular momentum, about any point of a single particle moving with constant velocity remains constant throughout the motion. Okay, so that we have to show that angular momentum about any point of a single particle moving with constant velocity remains constant, right? You see this picture, ma? So here you can see that that is what particle P. No, this is what capital M, the name of the point, and you know it is what r sin theta, right? It is r sin theta. When this is r, it is r cos theta, and this is r sin theta. When this is r sin theta, this is also r sin theta. When this is theta, this is also becomes theta, right? So this is what about the picture regarding a single particle. right? Here in this picture, the particle with velocity v, at point P at some instant small t, right? But we want to calculate the angular momentum of the particle about an arbitrary point O, right? This is O, it is what? O. See that light and this point is O, okay, right? So about the point O, we are going to calculate angular momentum, right? So the general formula for angular momentum, that is what? L is equal to R bar cross M V bar. That is what? R bar cross M V bar. Actually it is what? MVR sin theta. It is what? MVR sin theta, but we are writing like in a vector, right? Then see here, its magnitude is MVR sin theta, where theta is the angle between R bar and V bar, as shown in the figure. This is what R bar and this is what V bar, right? So it is the angle theta. Next, although the particle changes position with time, the line of direction of V remains the same. And hence OM is equal to R sin theta, okay. It is what? Is a constant. The line of direction of V remains the same, and hence OM is equal to R sin theta is a constant, okay, right? Next, see here, further the direction of V bar, the direction of L bar, L means what, angular momentum. See here, further the direction of angular momentum is perpendicular to the plane of R bar and V bar. This is the plane of R, it is R bar, it is V bar, So this direction of angular momentum is perpendicular to the plane of R bar and V bar, right? Okay. It is into the page of the figure. So like this, right? It is into the page of the figure. Next, this direction doesn't change with time. This direction, that is what? Direction of angular momentum doesn't change with time. Okay, right. Thus, angular momentum remains the same. Angular momentum remains the same in magnitude. Angular momentum remains the same in magnitude and direction, and is therefore conserved. Okay, full stop. Is there any external torque on the particle? Right, it's okay. So we talked about magnitude of angular momentum and direction of angular momentum, whether the direction is changing with time or not, everything is okay. And at last, I already told you, angular momentum remains the same in magnitude and direction and is therefore conserved. It is what? Like law of conservation of angular momentum, right? The problem is over. But here we had a little bit question, that is what? Is there any external force on the particle? Right? So one thing is position vector, another one is velocity vector, right? And angular momentum just now we calculated. The question is there any external force on the particle? Is there any external force on the particle, right? See here. Now, to answer this question, we are going to discuss the topic equilibrium of a rigid body. Equilibrium of a rigid body, right? So what is rigid body? What is rigid body? We know, and we have to know what is equilibrium. What is equilibrium, right? And here totally we are going to discuss about what is equilibrium means in the chapter of, that is what, laws of motion I told you, just what is equilibrium, right? But here our discussion is equilibrium of a rigid body. Equilibrium of a rigid body, okay, right? So now we are going to concentrate on the motion of rigid bodies rather than the motion of general system of particles, general systems of particles, right? Our concentration is mostly on motion of rigid bodies. See here, we shall recapitulate what effect the external forces have on a rigid body, right? We shall recapitulate what effect the external forces have on a rigid body, right? And What effect of external forces on a rigid body means? What is that? Effect of external force on a rigid body. You know what is the difference between external force and internal force? And in another direction, what is conservative force, non-conservative force? At the same time, different types of forces, that is what mechanical force and gravitational force and electrostatic force, right? So these and all we had, right? We had information about that. Basically, nature and situation where which type of force is going to act. So here we are going to omit the term that is what external, because we have to define it otherwise. That is what we shall deal with external forces and torques, right? So anyhow, here you just keep in mind, here we are going to talk about the effect of external forces have on a rigid body. That's all. Effect of external forces have on a rigid body, right? Next, the forces change the translational state of motion of the rigid body. The forces change the translational state of the motion of the rigid body. That is, they change its total linear momentum. You know, translational state of motion of the rigid body means what? That is, they change its total linear momentum in accordance with equation. Now, dp by dt is equal to F external. But this is not only the effect the forces have. You know, what about the torque? See here, the total torque on the body may not vanish, right? The total torque on the body may not vanish. So see here, what is the equilibrium of a rigid body means? Here we shall recapitulate what effect the external forces have on a rigid body. So we already have an idea what effects the external forces have on a rigid body, right? But now what I am saying is, the forces change the translational state of the motion of the rigid body. That is, they change its total linear momentum in accordance with this equation. That is what Newton's second law of motion, dp by dt is equal to F external. But this is not only the effect the forces have. So what about the rotational motion? See here, the total torque on the body may not vanish, even though you have this type of situation, right? But here you can say that the total torque on the body may not vanish. Such a torque changes the rotational state of motion of the rigid body. Such a torque changes the rotational state. Such a torque changes the rotational state of motion of the rigid body. Okay, that is what? That is, right? That is, it changes the total angular momentum of the body in accordance with, that is, it changes the total angular momentum. It changes the total angular momentum of the body in accordance with this equation. That is what? dl by dt is equal to tau external. dl by dt is equal to tau external. Okay, that is, it changes the total angular momentum of the body in accordance with equation dl by dt is equal to tau external. Okay, that is what we want to conclude here regarding the rotational motion and angular momentum. Okay, next, see this. A rigid body is said to be in mechanical equilibrium. You know what is meant by mechanical equilibrium? A rigid body is said to be in mechanical equilibrium if both linear momentum and angular momentum are not changing with time. Both linear momentum and angular momentum are not changing with time, or equivalently, whatever it may be. The body has neither linear acceleration nor angular acceleration. The body has neither linear acceleration nor angular acceleration. So what does it mean? See here, the total force, that is, the vector sum of the forces on the rigid body is 0, right? So here this means that the total force, that is, the vector sum of the forces on the rigid body is 0, right? So the point is here, total force, that is, the vector sum of the forces on the rigid body is 0. You can write like this. So here itself, what can I say based on this equation? If the total force on the body is 0, then what happens? total linear momentum of the body does not change with time. So what he told here, right? That is one thing. And so this is the condition for translational equilibrium. And if you go for rotational, this is the situation. That is what vector sum of the torques on the rigid body is 0, right? So here what is that? Total angular momentum, right? So in case of rotational equilibrium, that is what if the total torque on the rigid body is 0, right? The total angular momentum of the body, of the body does not change with time, right? So this equation, so whatever the equation we had here, that is what this is the equation. This equation gives that the condition for the rotational equilibrium of the body, right? It is for translational equilibrium, it is for rotational equilibrium, and it is the condition for translational equilibrium, and it is the condition for rotational equilibrium. These two equations we have to keep in mind. So whatever the information he is saying from here onwards, so with the help of these equations we cross checked and we verified like that. Okay, so to satisfy this information, these are the equations we can write. Next, see here, right? See here, equations 1 and 2. So these two equations, equations 1 and 2, both are vector equations, because force is a vector, torque is also a vector quantity, right? And they are equivalent to 3 scalar equations. And you can write like this. See this, that is what equation 1 corresponds to. So he is writing in terms of 3 axes, that is what x axis, y axis and z axis, right? So sigma I is equal to 1 to n, Fix is equal to 0. Sigma I is equal to 1 to n, Fiy is equal. This is the component along y axis like that. And here it is what the z axis, right? So like that we can write 3 scalar quantities corresponds to equation 1. These 3 are the scalar equations. Similarly you can write for equation 2. See what is the equation 2, and similarly you can write. That is what, because here we told what we told, linear momentum and angular momentum are not changing with time. Okay. Here this Fix, Fiy and Fiz are respectively the x, y and z components of the forces Fi. Next, similarly this is what here tau Ix, tau Iy and tau Iz are respectively x, y and z components of the force, x, y and z components of the torque, because here it is force, here it is torque. So here what I am saying is, regarding this one and this one, this is what regarding the force and this is what regarding the torque. The situation is same. So whatever here it is regarding, that is what Newton's second law of motion, and that is dp by dt is equal to F external and linear momentum. Next, this is what same like that, but in case of rotational motion, right? In case of rotational motion, and it is what torque. It is the product of position vector and force vector, right? And based on that we are writing here. The torque is analog of force. A force in case of translatory motion and torque in case of rotational motion. Okay, that is the only difference. And observe these two equations just now we have written, that is what equation 3 and 4. This equations 3 and 4 gives 6 independent conditions to be satisfied for mechanical equilibrium of a rigid body. These two equations gives 6 conditions, 1, 2, like that. Okay, 6 conditions, right? These two equations gives 6 independent conditions. There is no relation from one condition to another condition. 6 independent conditions to be satisfied for mechanical equilibrium of a rigid body. So here we are talking about mechanical equilibrium, right? See here, in a number of problems, all the forces acting on the body are coplanar. So what is meant by coplanar vectors? The vectors which are present in the same plane are said to be coplanar vectors. For example, it is the board. So there is one vector A bar and another vector B bar, another vector C bar. Now these three vectors are said to be coplanar vectors, right? So here what he is saying, in a number of problems, all the forces acting on the body are coplanar. Next, we need only three conditions to be satisfied for mechanical equilibrium. I told you 6 independent conditions to be satisfied for mechanical equilibrium, right? But regarding the situation, what is that? All the forces acting on the body are in coplanar. So here I am saying we need only three conditions to be satisfied for mechanical equilibrium, right? So what are these three conditions? Two of these conditions correspond to translational equilibrium, and the sum of the components of the forces along any two perpendicular axes in the plane must be 0. The condition, listen the condition carefully. Condition I am saying, right? So what is the condition? The sum of the components of the forces along any two perpendicular axes, in the plane must be 0. Right? This is the condition, I mean regarding the two conditions. And third condition corresponds to rotational equilibrium. Two conditions correspond to translational equilibrium, and third condition corresponds to rotational equilibrium, right? That is what the sum of the components of the torques, along any axis, perpendicular to the plane of the forces, the sum of the components of the torques along any axis perpendicular to the plane of the forces must be 0, right? There is a relation, in case of rotational motion, whatever he is explaining, he is comparing with translatory motion. That's why if we understood translational motion clearly, the understanding of rotational motion is easy, right? Even here also he is comparing, that is what the conditions what we got in case of translational equilibrium, and the conditions belongs to the rotational equilibrium, okay? So in translational equilibrium, what is the condition? The sum of the components of the forces along any two perpendicular axes in the plane must be 0. In case of rotational equilibrium, the sum of the components of the torques along any axis perpendicular to the plane of the forces must be 0. Perpendicular to the plane of the forces must be 0. Okay, right. Next, see here, the conditions of equilibrium of a rigid body may be compared with those for a particle which we considered in our earlier chapters. That is what in our previous chapters before this. Okay, and one more very important thing is here, the consideration of rotational motion does not apply to a particle. Only the conditions for translational equilibrium apply to a particle. Thus, for equilibrium of a particle, the vector sum of all the forces on it must be 0, right? Because since all these forces act on a single particle, they must be concurrent. Equilibrium under concurrent forces was discussed already in our previous chapter, right? So basically here I want to recap once again what is meant by equilibrium. I already told you in the chapter of laws of motion, but once again I want to say more because the situation came, right? Sorry for repeating. And see here, equilibrium means, the net force acting on the body is 0. The net force acting on the body is 0. Forces are acting, but the net force acting on the body is 0, right? That is what I want to say here. Okay, next, see this. See here, they have given two examples to observe the equilibrium, and see this example. So based on these two pictures, I can say one more sentence, that is what a body may be in partial equilibrium, that is, it may be in translational equilibrium and not in rotational equilibrium, or it may be in rotational equilibrium and not in translational equilibrium. That is we are calling it as partial equilibrium. equilibrium, right? And now you see these two pictures. Now, first you see this picture, I will tell you that is what it is a light, right? A light rod AB, negligible mass, at the two ends of which two parallel forces, see this is what and this is what, two parallel forces, and both are equal in magnitude, perpendicular to the rod, see here, perpendicular to the rod, you can see this picture, right? Now, you know, C be the midpoint of AB, comma CA, it is AB, and okay, so C is the midpoint of AB, and you can say that CA is equal to CB, CA is equal to CB, and we also used a letter to represent, that is CA is equal to CB is equal to small a, right? Okay. The moment of the forces at A and B, the moment of the forces at capital A and capital B, both be equal in magnitude, that is what here AF, right? Both be equal in magnitude, but opposite sense as shown in the figure, that is what, now you have to see this picture. So that is previously this is one and this, there is a lot of similarities, but there is also major difference, that is this is. So you see the position where the forces are acting, okay. So if you see here, the net movement of the rod will be 0, where the system will be in rotational equilibrium, but it will not be in translational equilibrium, right? Here, you know, the force at B, this is what this is what in figure A is reversed just in this figure. That is the only difference, no? That is the only difference between these two figures, right? So we have the same rod with two equal and opposite forces applied perpendicular to the rod. So one at end A and another one at end B. Here the moments of both forces are equal, but they are not opposite. Opposite means here it should be, but they are not here. So separated by certain distance. So they act in the same sense and cause anti-clockwise movement. Otherwise anti-clockwise rotation of the rod, right? The total force on the body is 0 here. So the body is in translational equilibrium, but it is not in rotational equilibrium. See here, but it is not in the rotational equilibrium. Although the rod is not fixed in any way, it undergoes pure rotation. That is what? Rotation without translational, right? Not only my explanation, if you observe these two pictures clearly, you can get some of the valuable information into your mind, right? That information is important for you, not only for writing and not only for reading and not only for listening. You think of these two pictures, right? So what happens if you do like this? You can do this small thing by taking a stick and asking them to apply force, and what will happen that you can experience personally, okay, right? So here I want to say some of the information, that is what, observe carefully. A pair of equal and opposite forces with different lines of action, is known as a couple or torque, okay. So a couple produces rotation without translational. Okay. That is what he is saying. This is the point we have to underline actually. A pair of equal and opposite forces with different lines of action is known as a couple or torque. Okay. A couple produces rotation without translational. Okay. Not only this example regarding the couple, you know, water bottle cap is there, opener, water bottle cap, right? So while opening the cap or closing the cap also, you are doing the same thing what we are experiencing here, right? That is like another example, okay, right? So in this class, we focused to discuss two example problems, that is example 7.5 and 7.6. Afterwards, we went to discuss equilibrium of a rigid body, right? So what is equilibrium? Already theriyumu. Here our interest is just to discuss the equilibrium regarding the rigid body and rotational motion, and what about the role of torque, okay, and what is meant by couple, right? So these are all only our interests, okay. Thank you. In the next class we will continue.